Hey, in this video, I want to get us used to a new kind of space. However, it is a subspace of Rn, so back to where the objects are actually vectors like we are used to working with. So I'm going to let A be an n by n matrix, and I'm going to let this variable lambda be a scalar, a real number scalar. And then I'm going to define a space, and I'm going to represent it by E sub lambda of A. And it's going to be a space consisting of vectors V in Rn, where remember A is an n by n matrix, such that A times the vector V is equal to some lambda times V. And so here, lambda will be some fixed value that you're given, and your matrix A will be a fixed matrix that you're given, and from there you'll be able to determine n. And so here, I'll have my matrix A, I'll have some value like 5, and what I'm looking for are vectors such that if I take A and multiply them by that vector, it's the same as if I had just multiplied that vector by a number. And so, quick example, if A is equal to 1, 6, 5, 2, and U, alright, yeah, I'll let U is equal to 6 minus 5, then A times U is equal to negative 24 times 20, but that's the same as negative 4 times U. And so I can represent U in both ways. And so if I were using this as my matrix A and negative 4 as my lambda, then n would be 2, and this vector U would be an element in this space. Okay, but what I want to do here is I want to actually argue that this space defined in this general way is in fact a subspace of Rn. So clearly it's a subset of Rn, but now I want to argue that it is a subspace. So I'll leave that definition there, and I'm going to claim that this space, E sub lambda of A, for any lambda, any A, is a subspace of Rn. And so to do that, I need to prove the three things. And the first is that the 0 vector is an element of this space. And so I can see that it is because if I take A times the 0 vector, that's equal to the 0 vector, which is equal to lambda times 0, no matter what A is, no matter what lambda is. And so this implies that the 0 vector is in my space as I needed. Okay, and second, let's suppose that I have two vectors U and V in my space. Then I want to show that U plus V is in this space. And for that, I'll do what we've done before, which is see what U and V being in this space tells me. So if U and V are in this space, then that implies A times U is equal to lambda times U, and it implies that A times V is also equal to lambda times v. And so maybe this doesn't seem, or it seems a little odd that this could be true for two vectors. But notice up here, this -4, so u is an example of a vector that meets that. So a times u is equal to -4 times u. But so is the 0 vector. So a times 0 is equal to -4 times 0 vector, which is equal to 0. So it does make sense to say there can be at least two things in this space, and it's going to turn out that there can be infinitely many. Okay, but now I want to show that u plus v is in my space. And to do that, I just need to show that a times u plus v is equal to lambda times u plus v. And I can't do that right away, but I know that if I take a times u plus v, that's equal to a times u plus a times v, since this multiplication of a times a vector has the distributive property. But because u and v are in my space, I know these two facts above, so this is equal to lambda times u plus lambda times v. And now since lambda is a scalar in R, I can factor it out. So I get this is equal to lambda times u plus v, and that implies that u plus v is in my space like I needed. Okay, and lastly, and this follows very similarly, if I have u in my space and c in R, then I want that c times u is in my space. And again, this up here implies that a times u is equal to lambda times u. And so now I just need to see what happens when I take a times c times u. And I want to show that this is equal to lambda times c times u. And if I do this, again, based on the properties of scalar multiplication with matrices, I can pull that c out in front. So this is equal to c times a times u. But again, I know what a times u is. That's lambda times u. And now, again, with the commutativity property, so this is a scalar, this is a scalar, I can rewrite this as lambda times c times u. And that implies that c times u is an element of my space. And therefore, this is in fact a subspace of Rn.